Now let's look at Newton 2. This is the one everyone talks about. The acceleration of a body is proportional to the force acting on it, i.e., we can write an equation that some number times force is equal to acceleration. So, first of all, acceleration is a vector. So if we're taking a number and multiplying it by a quantity and getting a vector, the only way to do that is with this scalar multiplication. So if acceleration is a vector and this number is a scalar, this thing here must also be a vector. So the first implication of Newton 2 is that force is a vector. The second implication is that force is instantaneous. We said that acceleration, what we were worried about in the previous slide, is an instantaneous process. It's how the velocity is changing right now. And if acceleration is instantaneous, then force must also be instantaneous. It happens right in an instant. It's a force acting on a body at a moment in time. And finally, we have this quantity 1 over m. So what does this tell us? Well, if m is really big, then m times a vector f is going to make that vector really small. The acceleration then is going to be a small number. M is the scalar. It scales the length of f. So if m is large, 1 over m is small. Big M means little a. On the other hand, little m means big A. And this is what we mean when we say that m, which is called the mass of the body, is a measure of its inertia. So we say that a system wants to move in a straight line. You have to put a force on it, F, and that will get it. So here's our velocity moving this direction. We've put a force on it this way. And that causes a change in the velocity. So the velocity now is in another direction. Well, you can imagine if I have a much bigger body moving with the same velocity and I hit it with the same force, I don't get nearly as much of a change in direction. So this is my initial velocity and this is my new velocity, and it doesn't change nearly as much as when I did this with the little one. So this one has small mass and this one has large mass. Okay, so mass is a measure of the resistance to an acceleration. It's the measure of a resistance to a change in velocity. And that quantity, that property is called inertia. The inertia of a system is its desire to follow the first law of Newton. It wants to keep going on a straight line, and the more it wants to keep going on the straight line, the more force you have to apply to it to knock it off of that straight line motion, the larger its mass is. This is why we call it the inertial mass. So the mass of a system is again a measure of how how strong a force we need in order to cause a particular amount of change in a velocity. So this equation is typically written F is equal to ma, but that's a little bit misleading. Really, it should be read this way: that we know a force. We take that force and divide it by the mass of our object, and that will tell us how the object is accelerating. This is incredibly important. This is maybe the most important thing, and this is one of the big things that all the people out there talking about the science of the physics of archery are missing. They are getting this part wrong. Ma is not a force. Mass times acceleration is not a force. A force must be determined first. Forces are things that act in nature. They're pushes and pulls on objects that occur in nature. You know the force first, and then Newton 2 tells you how the motion of the particle will change. It will tell us how the body will accelerate. You don't start with the acceleration and get from that a force. It's the opposite way. You start with a force, and then that tells you the acceleration. So force is given by a force law. It's given by some other thing entirely. So there's a couple of examples of force laws. For instance, a spring. If you take and pull a spring, grab a spring and pull on it, you'll feel a force pulling back at you. And so a simple force law for a spring is minus kx. K is called a force constant. It's just a number. Delta x here is just the displacement of the spring. So what this says is that if you take a spring, okay, we've got a spring here, and you grab one end of it and pull it this far by amount delta x, okay, that's a vector because we're pulling it in a certain direction, that the spring will exert a force backwards. It's going to exert a force this way, and that force is going to be minus some scalar times the length or the vector that you pulled this way. The minus sign just means it's pointed the opposite direction. So this minus sign means the force is pulling this direction as opposed to this way. So that's a force law for a spring. Here's the force law for gravity in a uniform gravitational field. So gravity near the Earth, we would have that the force of gravity is equal to minus the mass of an object times this gravitational vector. This g is a constant vector called the gravitational acceleration. So these are just examples of force law. So what Newton's law says is once you know this, then you can write down, for instance, for a spring, we can say we take the spring constant, multiply it by the displacement, and divide it by the mass that we're attaching to this spring. And then if we let it go and this force is exerted on that mass, that will tell us how the acceleration will occur. Or it will tell us, another way of thinking about this is how the position will change with respect to time. We can use this to figure out what the second derivative of the position is with time. So that's what F equals ma is. F equals ma is not telling you what forces are. F equals ma is once you know a force, then how will your body respond to application of that force? Once we know what the force is of the spring and we attach it to a mass and let the mass go, that will tell us how the mass will accelerate, how it's going to move. That's what the force law is, and that's what Newton 2 does. And what we'll see is that a lot of people we're going to see that they're going to take Newton 2 and integrate it to get something called impulse. And they're going to apply this in the wrong direction. They're going to say momentum tells us how much force we have. And that's absolutely incorrect. And it's important that you understand this to see why that's incorrect, because it's not the acceleration that tells us the force, it's the force that tells us the acceleration. Okay, so I've belabored that point enough, but it's extremely important. It's fundamental to everything about how we understand it and work with physics. So this is really, really important.